Let's look at section 14.7, talking about triple integrals in other coordinates. Now, we've seen that when we have a triple integral over region Q with respect to volume, we can evaluate this using an extended version of Fubini's theorem as the triply iterated integral with respect to z, then y, then x. But we've seen in previous sections with the double integrals that we can change the coordinate system from the x, y, z coordinate system into the polar coordinate system. Here we have the 3D extension of that. We've seen this if you think back to chapter 12 and our cylindrical coordinates. Remember that when changing to cylindrical coordinates, we keep the same transformations that we had in trigonometry, namely x is equal to r cosine of theta and y is equal to r sine of theta. For cylindrical coordinates, z remains z. We simply redefine x and y in terms of r and theta, but keep the height defined the same way. Here we have an extra factor of r, which we saw when we saw transformations to double integrals, and that carries over here as well. Well, remember that if we're looking in 3 dimensions, we can change not only to cylindrical, but spherical as well. So here we see all 3 forms of common coordinate system. Now I say common coordinate system because there are other less common ones which can be used, but these are the ones that you see the most often. In 3 dimensions, we can designate things in the rectangular coordinate system, in the cylindrical coordinate system, or in the spherical coordinate system. Here, this notation gives us a few things. First of all, it reminds us that whenever you're changing into polar, there's this extra factor of r. Same thing for changing to cylindrical, since cylindrical is simply polar with an extra dimension. When you're changing to spherical, there's going to be this extra factor of rho squared sine of phi. Okay, so here we're just going to sort of take this as a granted. In a previous section, we derived this extra factor. Here, for now, we're going to say this is just an extra factor that could be derived the same way. In the next section, we'll actually see where this comes from. But for now, we're just trying to familiarize ourselves with the transformations from one system to another. Okay? Here, whenever you're changing into polar, x is equal to r cosine of theta, y is equal to r sine of theta, and z is equal to, well, z. Here, x is equal to rho sine of phi cosine of theta, y is equal to rho sine of phi sine of theta, and z is equal to rho cosine of phi. Right? So here, this gives us not only, oh, by the way, don't forget this extra factor, but the notation also reminds us what our transformations are in case it's been a while and we have forgotten. Finally, here, these notations, the letters, just sometimes people forget what those are called. So let's just remind ourselves of that. This is pronounced rho. This is pronounced phi. All right. We know theta, but let's just remind ourselves that's theta. Okay. And let's remind ourselves of what these mean. Whenever we're talking spherical coordinates, rho is going to be the distance away from your pole, from your center, from 0, 0, 0. So here, this is simply a distance from the origin. It's not a directed distance, mind you. It's just a distance in any direction. Here, phi is going to be an angle relative to the z-axis, thinking in the xyz coordinate system. Phi would be an angle relative to the z-axis, where the z-axis would be the angle 0. And here theta is an angle relative to the x-axis on the xy plane. Note here, this one isn't on any particular plane, it's simply in any direction. But here theta is relative to the xy plane. So before we start off looking at how we transform our coordinates into one another and how to do the computations, let's take a minute and look at just some examples of what these objects represent in space. Because the objects that we can sketch out will often help us in determining what these boundaries are, or in some cases, whether or not our boundaries can efficiently be stated in a particular coordinate system. So let's consider the following. Recall that if you take the triple integral over a region Q, dV, that's equal to the volume of Q. Okay. Well, now up here, we see that, okay, it can be done as we did in previous sections, but it can also be done in any of these other coordinate systems. So here, let's go ahead and take an example. And here we're not going to complete the integral. We're simply going to sketch the region. We want to see, okay, let's make sure we understand what these are actually telling us. So example, let's sketch the region. Let's sketch the solid Q, whose volume is given by the integral from 0 to 2 pi of the integral from 0 to the square root of 3 of the integral from 0 to 5 minus r squared r dz dr d theta. Okay. Now you might think, okay, so that extra r is going to do something, right? Because usually it's supposed to be just the triple integral dv. But remember, whenever you're changing from rectangular into polar, this extra factor comes out, which means that here, this f is just the number 1 in this case. This is 1 times all of this stuff. But all of this stuff is inherent to the triple integration in polar coordinates, in cylindrical coordinates, should I say. So here, this f would be, well, just the number 1. So here, this extra r isn't doing anything other than telling us, okay, here's that extra factor that would have been necessary to convert one function in rectangular into a function in cylindrical. And hence, this is still the volume. Okay, so we want to sketch out this region. Notice I'm not actually trying to find the integral. We can if we want to, but here we're just going to give an illustration. So the first thing we want to do is we want to say, okay, 3D is hard. Let's start with 2 dimensions. Note that in these 2 dimensions, we're basically back in polar coordinates, back in Cal 2, or I mean, really back to trigonometry when we first learned about those. So here, if you look at just this part right here, that's going to be an object on the plane. All right, so here this describes a plane region, meaning just 2 dimensions. So here, let's describe just that plane region. Here, it doesn't just describe a plane region, it describes this one. Okay, so here is my plane, right? Here's my x and here's my y. And you say, well, it's r and theta. Well, yeah, but r and theta are going to give you values to express an object. That object is still on the xy plane, though. It's still in 3D. So here, we're going to say, okay, I want a value of r to go from 0 to the square root of 3. Okay, so remember, r in polar coordinates means the distance away from the pole, from the center here. If you want to go from 0 up to the square root of 3, that means you want to start at 0, and you want to go out as far. The furthest distance you should get to is the square root of 3. Okay, but now, is it only in this direction, or is it only in this direction? Which direction should I go? That's what this tells us. Here, theta goes from 0 to 2 pi. Oh, well, 0's here, and then this would go out to pi over 6, pi over 4, pi over 3, pi over 2, and it would keep going around to pi to 3 pi over 2 until eventually we get back to 2 pi. Whenever you see theta goes from 0 to 2 pi, all that means is go all the way around. So here, this would be on the plane. It would be the circle, or I guess I should say the disk, because it does include all the stuff inside, from 0 out to the square root of 3. Okay, so this is a disk of radius square root of 3. Okay, so now that I have my disk, what that tells me is that my object will exist over this disk. Whatever I have, whatever this z tells me, might exist a bunch of places. We only care about the part that's directly over this circle. Hence the name cylindrical, right? If you take this circle and just care about whatever is above it, well, then you end up with a cylinder. Right? Now, that cylinder may have a wavy top, but it's still basically a cylinder. Anyone who ever took a Coca-Cola can and left it in the refrigerator for too long or in the freezer and didn't have it explode, but had the top bulge out, that's what you're looking at. It's still a cylinder, a can, but the top might be wavy and bulgy. All right, so whatever we care about is going to be over this cylinder. So now let's consider the third dimension. Let's consider z here. Okay, so now by putting this in, our entire region, okay, we'll note that what we care about is still over that circle or that disk, right? Because it does care about the things inside. So here we're going to take the circle of radius root 3, and we're putting it on the third dimensional grid here. We're putting it on the XYZ coordinate axis. So here I've simply taken this and said, okay, so that's going to give me the base of my object. Something like that. Okay, now, how far up above this does it go? Well, notice what your other boundaries are. This one says z, which is the height, is equal to 0. That's the lowest it ever gets. Okay, so when z is equal to 0, that means you're on the xy plane. So not only are you over this disk, you're actually coming down all the way to this disk. So you're going to start from here and go only upwards. You say, okay, well then how far up am I supposed to go? Well, let's see. Notice this upper bound, 5 minus r squared. Notice that's parabolic. It's a parabola. So here, let's consider just something that looks like this. If I have z, and here's r, and you say, well, wait a minute, I thought it was x and y. It will be in just a moment. But here, let's think about it this way, just to take advantage of that variable that I have now. 5 minus r squared would look something like this. It would be a parabola that faces down, and it would have a maximum height of 5. All right, so this would be 5, I guess 0, comma 5. Okay. All right, but so what? Well, notice that if you are placing this on the three-dimensional coordinate system, r just means how far away are you from the center, from the pole here, right? That's what r meant before. R means the distance from the center to the outside. Okay, so here, this r is this r. And z is z. And you say, well, wait a minute. How are you saying that's r? That's x and that's y. Well, sure, but r just means the distance from the center outwards. We don't say in what direction. So we could say, oh, well, it's in this direction along y, or we could say it's in this direction along x. But that's giving us traces, isn't it? That's giving us what we need to form our graph. Here, let's see. If this is 0, comma 5, if I want my z to equal to 0, that would make this the point root 5, comma 0. And that would make this the point minus root 5, comma 0. Because here, if you plug in root 5 or negative root 5, 5 minus root 5 squared would give me 0. Okay, so that means that I have my z will go up as far as 0, comma 5. Okay, so that means that this will go up as high as 5 steps, just like that. And now, if I go out as far as the square root of 5 units, that'll bring me back down to the plane. And that'll be true in every direction because, of course, here R is true in every direction. It's a circle, so it doesn't matter which direction I look. So that means if I extend this down onto the y plane, it's going to come down. Remember, this was the square root of 3 right here. Here, that's going to go out a little bit further. That's going to go out to the square root of 5, which is fine. And then over here, it's going to do the same thing. We're going to have a parabola. That's the square root of 5, or negative root 5. And the same thing this way. And the same thing that way, in every direction. Oh, but remember, we didn't care about it forever. We just cared about it over this thing here, over this region. Oh, okay. So that means that from here, we're going to go straight up until we reach that parabola. And from here, we're going to go straight up until we reach that parabola. And from here to the parabola, and from here to the parabola. Notice that that's now got straight sides, but now the top has a kind of a bubble shape. Right? So here what I have is I have this object. Here this looks like a cylinder in the traditional sense, as in like a soda can, but then the very top is bulging out in a parabolic shape. This looks, I don't know, to me this looks like a cupcake. It's a little cylinder with a little dome top. And so the solid Q that we're describing is all the stuff inside the cupcake. And now I'm hungry. Oh well. All right, let's do the same kind of exercise, but now let's do it for cylindrical. This was cylindrical. Let's do it now for spherical to get an idea of this one. Usually cylindrical isn't terribly difficult because you have a lot of experience with the polar coordinate system. That'll allow you to get 2 of your dimensions, and then your third dimension is just something that projects upwards or downwards from that. So cylindrical is usually not terribly difficult to express as an illustration. The spherical coordinate system can be complicated, but when it is simple, it is exceedingly simple. Meaning, if we use it at the right time, it does make things a lot better than if we didn't use them. So let's consider the problem, same kind of problem. Let's sketch the region. Let's sketch the solid Q. And again, we're not going to perform the integral. We're just trying to talk about the object. Sketch the solid Q whose volume is given by the integral from 0 to 2 pi of the integral from 0 to pi over 4 of the integral from 2 up to 5 of rho squared sine of phi d rho d phi d theta, just like that. Again, just like with the cylindrical coordinate system, note that this r is an inherent part of the transformation. This r isn't saying that's an extra function. This is an extra factor that you get when you convert from rectangular to cylindrical. Likewise, when you convert from rectangular to cylindrical, you get this extra factor of rho squared sine of phi. So here, that rho squared sine of phi isn't something that you're considering as an external function. So here, we're simply trying to sketch out what this is saying. Okay, so let's go ahead and do that. Notice here, the integration would actually be really, really simple. All of these boundaries are constant, so it would just be a matter of integrating first with respect to rho, plugging in the numbers, then with respect to phi, plugging in the numbers, and then finally with respect to theta. So here, if you want to try the integral, it's trivial. It's very, very short and doesn't have anything other than basic integration rules. Here, what we concern ourselves with is the solid. Okay, so now one nice thing about spherical is that at least we have one variable that is familiar to us. Here, theta is the same theta that we're familiar with. On the xy plane, it's telling you from your x-axis is equal to 0, pi over 2 is straight up, pi is Going back the other direction, straight down is 3 pi over 2, and then back full circle is 2 pi. So just like in the previous example, having theta go from 0 to 2 pi just means you're going to go full circle around. Okay, so the one nice thing is at least this one is still familiar. If it's from 0 to pi, then you're doing a half spin, half circle. Okay. So we still want to look at two variables at a time. Just like in my last example, I started off by saying, okay, let's consider these two, and we'll have something in the polar coordinate system which we can then project. We're going to do something similar here, except we're not going to start with these two. Now, we can, but I'm going to start with these two. I'm going to see what they describe. Okay. All right, looking at just this right here. The reason I'm looking at just this right here is now I don't have to worry about a full 3 dimensions. I only need to worry about what's happening here. Remember what this says. Rho tells you that from the origin, you're only going out as far as this and this. That's your distance. Phi is giving you an angle starting from the positive half of the z-axis. So eventually I'm going to want to draw this. I'm going to want to draw this in 3 dimensions. But for right now, I'm going to take just 2 dimensions and look at those. One dimension that I'm going to want is z. I definitely want to look at this because that's how phi is defined. Rho is defined in every direction. So it doesn't matter what other dimension I take. So right here what I want to do is I want to take a look at just one trace. I want to look at just the, I can either do the xz trace or I can do the yz trace. And because it's my choice, I'm just going to choose YZ because personally I feel that's easier to draw. But again, that's just a personal choice. So here, let's take a look at these two and look at them just on the YZ plane. Okay, remember how phi works. Phi says the angle 0 is pointing straight up toward the z-axis. Okay, very nice. All right, now this angle is starting from 0 going outwards. So this would be 0. This one over here would be pi over 2. So pi over 4 would be halfway in between those. Pi over 6 would be right there, right? 0, pi over 6, pi over 4, pi over 3. It's kind of the opposite, or not kind of, it's the opposite as of the angle that you would normally consider in trigonometry. We're going this way. So this is the angle. Phi is equal to 0. Phi is equal to 0. And here I have phi is equal to pi over 4. Okay. Now, rho tells me, okay, phi has given me some boundaries. I have to stay within these 2 lines here. Okay, but now rho tells me how far I can go within those 2 lines. Okay, so rho is equal to 2. All right, well, here's 0. I don't want to be between 0 and 2. Okay, here's rho is equal to 2. It's a circle of radius 2. Now, of course, we don't want the full circle. We only want the part of the circle that's inside of those rays. So here that would be a radius of 2, but we don't care about this part out here, just in here. Likewise, we could have a circle of radius 5. And again, we wouldn't really care about the full circle of radius 5. We would only care about the part that's between these 2 rays. So this would be a radius 5. And so the region that I care about is this stuff in here. Okay. So looking at just rho and phi, I have this sector, this piece of a sector. It's the, you have a slice of pizza and you're taking a really, really thick crust. Okay, you're taking just that crust. Yeah? If y'all couldn't tell, I'm actually very hungry. I skipped breakfast this morning. So we're going to take this, and now we're going to take theta and have this projected outwards into 3 dimensions. So let's consider this object over here. After all, it looks something like this. And here I'm going to draw this first part in pencil, but that's mostly just because I'm going to erase it. I'm going to take this and this, this, and this. All I've done is I've replicated this image, right? The wedge with the outer line and the inner line. And now the part that I really care about is this stuff in here. And this is on the YZ plane. Okay, but now this is simply giving us a rotation. Thinking back to Cal 2, you remember the solids of revolution? You have an object and then you start making it spin. That's exactly what's happening here. Here you have a flat object, but now you're going to have it spin. Remember, theta starts from here and goes around and around this way, which means that it's spinning in the XY plane, which means the axis of rotation would be Z. So here, basically, just imagine this is going to start spinning around Z. Oh, okay, so that'll give me my illustration. Here I'm going to draw this in pencil, but again, that's mostly just because I'm going to erase part of it here in a moment. So something like this, and it would be rotated around this way. So that's our object. Our object is this shape here. These, of course, are just there to guide me, but they're not actually part of my graph. So my object would look something like this. It would have a bubble top, and in here it would be indented as a bubble as well. And here it would have these slanted sides. Here, this is a spherical top, and inside it would be indented also as a sphere. So there'd be a little bubble forming up from the bottom, like that. Once we have an idea as to how we can represent and how we can interpret these things physically, and vice versa, how we can take something physical and interpret it in, this way, we can use that to our advantage. Because there's going to be several problems that when you try to evaluate them using the typical rectangular coordinate system, it's going to give you some very difficult problems. Mostly because the integrations would either require several substitutions, one within the other, or just because the integration is something very, very long. So here, we're going to take an example, and this is going to be an example that serves, I'm going to use it for a couple of things. It's going to serve a few purposes. So let's begin with, so consider, let's see here, let's consider the integral from 0 to 2 of the integral from 0 to the square root of 4 minus x squared. Whenever you start seeing sums and differences of squares under square roots, you should start to get nervous, because that means that in rectangular, things are going to be unpleasant. And here, that's going to be square root of 16 minus x squared minus y squared, like that. Now here, we're going to take square root of x squared plus y squared dz dy dx. Just like that. All right, so now I haven't asked anything about the problem. I've just said, hey, here's an integral. Now, one thing I could ask you to do is to just integrate that, which would be not very pleasant at all. So what we're going to do here is we're going to use this example for a few different problems. First of all, we're going to convert this into rectangular. Sorry, that's already rectangular. We're going to convert this into cylindrical. We're also going to convert this into spherical. Once we have both of those conversions, we're going to look at them and we're going to see, okay, which one looks simpler. Many times it'll be very, very obvious which one is simpler. Once we figure out which one is simpler, then we're going to finally go through and evaluate. So this is going to be a three-stage problem. First, convert to rectangular. Oh, sorry, I keep saying rectangular. First, convert to cylindrical, then convert to spherical, and then out of those two, whichever one looks nicest, let's go ahead and evaluate to get our answer. Okay. Usually, you wouldn't have to go through both of them. Usually by looking at the integral itself, you'll be able to tell which one is easier, either cylindrical or spherical. But since you don't know that yet, we're going to go through and talk about both of them and then compare and see why one was simpler than the other. Once you see why one is better than the other, it cuts down the amount of work you have to do. You wouldn't have to go through both. You would just pick whichever one is simpler. So here what I want to do is I want to go ahead and represent this. I basically want to do with this what I did before. I want to express it as a picture, as an illustration here. All right, so let's give this a try. All right, so let's go ahead and sketch the solid region Q. So I said this is a 3-stage problem. I guess it's a 4-stage. First of all, we're going to draw this out. So part 1. And this is for illustration, for lecture purposes. In a real problem, you wouldn't be expected to do all of this. You would be expected to evaluate the integral. And if you could do it that way, well, great. If not, well, then you would convert it to whichever one is convenient. You wouldn't go through all of this. This is for the sake of illustration. So here, part 1, let's go ahead and sketch the solid Q. All right, well, this gives me my height. This gives me my width and my length. Just like in previous problems, I don't want to consider all 3 variables at once. I want to consider 2 variables at a time. I want to consider a plane. So here, let me go ahead and consider just x and y at first. So first, consider the plane region. Let's consider the integral from 0 to 2 of the integral from 0 to the square root of 4 minus x squared dy dx. Notice I'm not caring about the function for now. I'm not getting to the point of evaluating. And here I'm only looking at these 2 outer ones. Okay, so let's sketch that. All right, well, that's not too bad. Here we get that y is equal to 0. Okay, that's the lower bound. We get y is equal to the square root of 4 minus x squared. Oh, well, here I could just go ahead and square both sides. So that gives me y squared is equal to 4 minus x squared. And then I can go ahead and add the x squared over here. And I note, oh yeah, that's a circle. Just like that. Okay. So what this does is it gives me the bounds on y. Notice that y goes as far down as 0 and as far up as the edge of a circle. Notice that's a positive square root. So even though this circle is got a part on top and a part on the bottom, here we only care about the upper part because that's going to be our upper bound. We don't want to go below 0. So here I have a circle of radius 2. Okay, I have a circle of radius 2. And I want y to go as low as 0. Okay, so no lower than this. And as high as the outer edge of the circle. So no higher than this. Okay, so I got to be bound in there. Oh, but now x has something to say. All right, we want to go as far right as 0. Okay, so we don't even want this back half. We want to go as far right as 0. And we want to go as far left as 2. Okay, so here this tells us we want the upper half. This tells us we want the right half. So this must be the part that we want. So whatever we want will live over this region here. Okay. All right, so now let's go ahead and take that into the 3rd dimension. Let's start off with this region here. Notice that it is a quarter disk. Here that's going to be a radius of 2 in every direction. And we only want the part that extends in this direction, where x is positive and where y is positive. So something like that. Yeah? All right, well now here, let's go ahead and talk about our 3rd dimension. Here we want z to be as low as 0. Oh, okay, so then that means that we want to go as far down as the xy plane because that's where z. Not only are we going to be above this object, we're actually going to come down and touch that object. So here z is as low as 0, and z is as high as the square root of 16 minus x squared minus y squared. Okay, well, I know what z equals to 0 means. That's the xy plane. That's just that one. But now this one, that does look familiar. Z is equal to the square root of 16 minus x squared minus y squared. Let's consider the actual boundary itself. If I now square both sides, that's going to give me z squared equals to 16 minus x squared minus y squared. And if I go ahead and move these over this way, that's going to give me x squared plus y squared plus z squared is equal to 16, which is a sphere of radius 4. All right, notice if x and y were both 0, if y and z were both 0, x would equal to 4. If x and y were both 0, z would equal to 4. And if x and z were both equal to 0, y would equal to 4. So it doesn't matter what direction you're looking in, you're always going to go out 4 units. So here we have a sphere of radius 4. All right, but now that sphere of radius 4, we want to consider what part of that sphere we want. All right, so here we have a sphere of radius 4. That's going to go, so here we already have 1, 2. I'm going to draw this part in pencil because I'm going to erase a big part of it in just a moment. Forget about this part. Let's just draw a sphere of radius 4. Okay, so that would go out 4 units in every direction. And this would go up and up to 4. And every one of these is the value of 4. It goes out 4 units. Oh, but remember, even though this sphere goes out that far, right, we're going to start from z is equal to 0 up to z is equal to square root of 16 minus x squared minus y squared. In other words, we want the upper hemisphere, the upper half of the sphere. We are also bound by this set of restrictions because our x value and our y value won't extend beyond this. So we don't even get to keep the entire hemisphere. From here, we can't go any further than this. Okay, so if that's as far as we can go, we can start with our circle, but we can't keep the entire circle, or sphere. We can't keep the entire sphere. The best we can do is keep all of the stuff that's directly above it. So this is our object. All right? This is our solid cube. From here, it seems like either one could work. After all, it's got a sphere on top, so spherical coordinates seem nice. On the other hand, it's got straight sides, so cylindrical coordinates look doable too. Whenever something like that happens, this takes precedent. If something looks like it could be either spherical or cylindrical, go with cylindrical. Cylindrical will be easier to express notation-wise, and it'll be usually simpler to evaluate. If you have a sphere and straight sides, treat it with cylindrical coordinates. If you don't have the straight sides, if you have just portions of a sphere and the sides are either also curved or slanted, then you can try spherical coordinates. But if it's an amalgamation of both, cylindrical is generally going to be simpler. Here I'm going to show you how to do both, just because you should know how to do both, and also because, well, even though this problem will eventually turn out to be simpler in cylindrical, other problems will be simpler in spherical. So here, let's go ahead and do both. All right, so let's go ahead and start off with spherical. I'm just going to redraw my image here, just so that we can have it handy. So part number 2 of this problem is to convert the integral, the triple integral, to spherical coordinates. I'm not asking you to solve it, we're just converting it to spherical coordinates. Okay. Here, I'm just going to redraw my illustration, and it was something like this. All right, so something like that. You have your cylindrical part, but then at the very top, it's domed. It's got a spherical shape on top. Okay, so let's go and convert everything to spherical coordinates. Well, first of all, one thing to note is that here, rho is going to be a little difficult to pin down. Remember, rho is the distance from the center out to the outermost edge of your object. But notice that your outermost edge of your object behaves two different ways. If I start from here and go to this part, well, this outer edge behaves like a sphere. But if I start from here and go out to this part, this outer edge acts like a straight line. So what that means is that rho can't be determined with a single function. Here, I'm going to have rho be one value here, or rather one kind of value here, and it'll be a different kind of value over here. So what that means is that my integral will have to be described with two separate pieces. One piece of my integral will have to be described, we'll have to describe this portion here where rho goes from this center to the dome, and here where rho goes from the center to a straight-sided cylinder. So here, note, this means that we're going to have two separate integrals. That won't always be the case. Here, if these side edges were completely uniform, if they were always spherical or always cylindrical or always whatever, parabolic, then you would only need one. But because here, rho can't be described by a single function, here I need two functions to describe it, one for here and one for here. So this is actually going to be the sum of two different integrals. I need to find each of them, to find each of these two, find this integral in here, find the integral of the stuff in here, and then add those together. So let me go ahead and describe these separately. Let me call the stuff inside of here, this looks like an ice cream cone to me. You got a cone with a little bubble top. Here I'll call this region number 1. And this stuff out here, which is the cylinder part, here it'll be missing a big gap in the middle, but whatever, it's still the cylinder part on the outside. I'll call this one R2. And here that's just region 1 and region 2. Maybe I should call them Q1, right? Because this is in 3 dimensions. So here, let's say Q1 and Q2. All right, so if we're going to integrate there, we need to describe each of them on their own. So this has now gone from being a single integral to being the sum of two separate integrals. Okay. Now, I need to convert my original integrand into spherical coordinates. Here, we didn't just have an integral dz dy dx, we also had this thing right here. Okay, so as we're converting not only our boundaries, but also our function and the differentials. Okay, so let's go ahead and do that. Here, we're going to take square root of x squared plus y squared. Okay. Let's convert the integrand, which was the square root of x squared plus y squared, to spherical. Okay. Now, we have conversions for all of those. At the very beginning, we saw that x in spherical is rho sine of phi cosine of theta, and y is rho sine of phi sine of theta. So here, I can write this as, so x is equal to rho sine of phi cosine of theta. Y is equal to rho sine of phi sine of theta, just like that. So that gives us that the square root of x squared plus y squared is going to equal to the square root of, that's going to be rho squared sine of phi squared cosine of theta squared plus rho squared sine squared of phi sine squared of theta, just like that. Here I can factor out, notice I have rho squared sine squared of phi on both terms. So I can write this as the square root of rho squared sine squared of phi. And when I factor that out, I'm left with cosine squared of theta plus sine squared of theta, which by the Pythagorean identity is just the number 1. So here that's the square root of rho squared sine squared of phi. And here I can go ahead and take the square root, which will give me rho sine of phi, which is nice, yeah? So here we can go ahead and write that as our integrand. So here when we're taking a triple integral, this is the thing we're taking the triple integral of. This is going to be rho sine of phi, and that's going to be rho sine of phi. Okay. Now, don't forget, whenever you're converting from rectangular to spherical, you also have this extra factor. So this is our function, which we just converted. But now you also have this rho squared sine of phi along with your new differentials. So here, there's going to be rho squared sine of phi. And that's going to be rho squared sine of phi. And then here, that's d, what did we do here? I'm going to go ahead and just do the same order that they have. You can write them in different orders, but then it really makes no difference. D rho, d phi, d theta. And same thing over here, d rho, d phi, d theta. Just like that. Okay. So we've converted. Here is our function. This was a integrating factor. I mentioned for now, just take my word on this, but in the next section, we'll show you where these kind of factors come from. And then here, since you're integrating, your boundaries will be different for these two, but the thing that you're integrating will be the same. So here, this is the same as this one. Okay. Incidentally, I do some of these problems ahead of time, especially the longer ones. When I first did this, I forgot the square right there. And I went through the entire problem and I just couldn't figure out why my problem was so wrong. I forgot that square right there. Of course, here you can write this as rho to the third sine squared of phi. You can write that as rho to the third sine squared of phi. But again, we're not going to evaluate this right now. We're just setting everything up. Okay, so now let me do my region 1 first, my Q1. Let's go ahead and talk about the boundaries here. Okay, so notice that we already know what theta is going to be, because here we know we're only taking a quarter of the disk all the way around. Yeah. In this illustration here, which we built, here we see we don't take the entire object. We only take the part which is over this part in the first quadrant. Okay, well, in the first quadrant, I know that angle's 0, and I know that angle's pi over 2. So here, theta is the nice one. It's from 0 to pi over 2, and that's going to be true for both of them, because whether I'm up here or down here, I'm still only considering things over this quarter disk. So here, that theta is going to be from 0 to pi over 2 for both of them. Okay, so that part's nice. All right, now what about this? Well, notice this is an angle phi, right? After all, phi starts from the positive half of the x-axis, and then we come down from there. But that is what an angle phi, that is what that would look like, right? This would be the angle 0. This would be the angle, oh, I don't know, pi over 4, pi over 3, pi over 2, something like that. Well, it wouldn't be pi over 2 because that would be down here. That would be on the x-axis. So here I know that's some angle. So now let me figure out what that angle is. Well, it seems to be wherever that dome and that cylinder interact. It's where they intersect. Wherever these intersect, that's where I'm going to find that angle. Okay, so let's go ahead and do that. Let's go ahead and find where this and this intersect. Well, that's not too difficult. After all, we know the equation to that dome. The upper sphere is going to be x squared plus y squared plus z squared equals to 16. All right, we had that from the previous step. Over here, we had the equation for the sphere of radius 4. And we have this object here, which is a cylinder of radius 2. We saw that as well. Here, this has a radius of 2, and it just comes straight on up. And we know what the cylinder of radius 2 looks like. After all, it's just the circle of radius 2 written as a cylinder, which has rulings in the direction of the z-axis, which means z is the variable that you're missing. So here we can write x squared plus y squared is equal to 4. You say, well, you only want a quarter of that. Oh, that's fine. Here we're just trying to find where the intersection is. This has already handled the fact that we only want a quarter of it. Okay, so here's our sphere, and here's our cylinder. Notice one of the variables is missing. That's what makes it a cylinder. And so now we can find where these intersect. And that one's pretty simple. Look, x squared plus y squared can just replace this one. So here, putting these together, I get x squared plus y squared is equal to 4. So this thing can be replaced by the number 4. 4 plus z squared is equal to 16, which means that z squared is equal to 12, which means z is equal to the square root, now it should be plus or minus, right? Plus or minus the square root of 12. Oh yeah, but here we only want z to be positive, right? We don't want z down here ever. Okay, so here we say, but since z is positive, right, we know that we want z up here, then that means that z must only equal to the positive square root of 12, which is the same as 2 root 3. Okay. All right, so now we know that this will intersect at a height of 2 root 3. Oh, but from here out is 2 units, right? We've seen that in our initial illustration. Here, from here to here is 2 units, but now we find that from here to here is 2 root 3 units. Oh, I have 2 sides of a right triangle. I can find out the angle. So here, let's take a look at that illustration. I have a triangle that looks like this and like this. The height of the triangle is going to be 2 root 3. I'm going to have the width of the triangle be just the number 2. And here I'm trying to figure out this angle, right? Because after all, straight up is 0. And then how far out I go from 0, that's the angle that I'm looking for. So here I want from here, with the angle 0, outwards from there. Okay, so that's my angle theta. Okay, well that's the opposite, that's the adjacent. The tangent of the angle theta is going to equal to, I guess I should say the angle phi, right? Tangent of the angle phi is equal to the side opposite over the side adjacent. Oh, okay, so here that means that phi is equal to the inverse tangent of 1 over root 3, which is just pi over 6. So here phi is equal to pi over 6. Oh, okay, so then that means that at the angle pi over 6, that's where my picture splits up. At the angle, I keep saying pi, at the angle phi equals pi over 6, that's where I transition from having this part of my object to having this part of my object down here. Oh, okay, so then that means this object is going to go from 0 to that pi over 6. Okay, so Q1 is from 0 to pi over 6. And then starting from pi over 6 on to I get to the x-axis, in other words, until I get to pi over 2, that is phi for my other function. So that's going to be pi over 6 up to pi over 2. All right? From 0 to pi over 6, that's the first one. But then picking up from where the other one left off, all the way until I get down here. 0, 90-degree angle. Well, that's pi over 2 right there. All right, so we're almost done with that setup. You'll notice that this one is very long and complicated. You'll notice I said before that if something looks like it could be either a spherical coordinate problem or a cylindrical coordinate problem, you want to go with cylindrical. Right? And this is part of the reason why. These take a while, because here, since it has both, you have to split it into 2 sections, which takes, well, twice as long. All right. Finally, the last thing is we want to find out about rho. Okay. For this one, rho is simple. For Q1, you're starting from 0 and you're going out to a sphere of radius 4. Oh, okay, so from 0 to 4. 0 to 4. Those are nice. That's just constant. From 0 up to 4. And no matter what direction you're going in, it's always 4. Oh, okay, so that's just constant from 0 up to 4. This one, on the other hand, is more complicated because looking at this one, I noticed that this distance from here to here is 2. From here to here is, or what did we say? It's not 2. Right? It's I can complete the Pythagorean theorem on that triangle and find that hypotenuse. Either way, that's longer than this. Actually, I guess it's 4, right? Because from here to here, that's the start of the circle, the start of the sphere. So the distance from here to here is 4. The distance from here to here is 2. And in between, well, it's going to vary. So unfortunately here I can't use constants. These are going to have to be variable. All right. So let's see. So that's the last thing we're going to need. Here, my lowest bound is still 0. Because notice, I'm going all the way down to the pole. So I'm starting from here and working my way out. So 0 is still my lowest bound. The highest bound is what I need to describe. I need to describe, how do I describe this cylinder using a radius, using rho? Well, it actually turns out to be not terribly difficult. It's just a matter of looking at the conversions between spherical and cylindrical. All right. So let's go ahead and recall. And I don't blame you if you don't remember this. I didn't remember it either. I had to go back and look this one up. This is all the way back from chapter 11. We had conversions between cylindrical and spherical, and the conversion was R is equal to rho sine of phi. Okay. Now that, once I looked it up, was exactly what we needed. If you're having a hard time remembering where that was, this was quite a while back. This would have been section 11.7, which due to recent events, that was about 8 weeks ago. But due to recent events, it feels more like 8 years ago. So here we have R equals rho sine of phi. But if we're describing this cylinder here, notice that this cylinder has a radius of 2. Okay, so yeah, generally I want to be describing R in terms of rho and phi. But here R is specific. This is a cylinder which has a radius. Remember, R is bound on just the xy plane. That has a radius of 2. Okay, so for my cylinder, R is equal to 2. All right, if we go back to our illustration from the previous part here, that radius is clearly 2. We don't take the full circle, but what part we do take, the radius is 2. So for my cylinder, R is equal to 2, which means that instead of saying generically R equals rho sine of phi, what I can say is 2 equals rho sine of phi. Oh, but what I'm trying to do is I'm trying to describe rho, right? That's what I'm trying to do. I'm trying to describe rho using variables either theta or phi or any constants. Oh, okay, so solve for rho. Here, I want to get rho by itself. Let me divide both sides by the sine of phi. So that's going to give me rho equals 2 over the sine of phi. And dividing by sine of phi is the same as multiplying by the cosecant of phi. So here we can write this as rho is equal to double the cosecant of phi. Oh, and there we go. This describes my cylinder but that's what I want. I want to be able to describe this cylinder as the outer bound. So here, this is the integral from 0 up to 2 cosecant of phi. And that is our result. That was a long one. You'll see the next one is going to be into cylindrical, and it will be considerably simpler than this. Okay, so let's take a look at the part 3 of this problem. Once again, remember, you wouldn't normally go through this many parts here. I'm just using this as one really big example. I'm doing everything that I can do with just this one. That way you don't see, oh, well, this particular function works this way for this particular kind of problem. No, just here's how it works all the way through. So part 3, let's go ahead and write this in cylindrical coordinates. Okay, so here we go. Once again, let's go ahead and draw our object. All right, so there we go. Here's our object. Again, we have a cylinder down here. We only want to consider the part in this direction. We only want all positive values, and we want everything that is above this quarter disk and below this part of the sphere. All right, so we're converting that. Notice here, this can all be described as a single cylinder from bottom to top. It always has the same bottom, namely that flat plane, and it always has the same top, namely this sphere. So here we can write this as a single integral, and we won't need to split it like we did for the spherical. All right, so let's see. Let's write down our original problem. That was the integral from 0 to 2 of the integral from 0 to the square root of 4 minus x squared. The integral from 0 to the square root of 16 minus x squared minus y squared, square root of x squared plus y squared, dz dy dx. Okay, so first of all, let's go ahead and talk about converting this integrand, because into from rectangular into cylindrical, this one's actually really nice. Recall that r cosine of theta, that's equal to x, and r sine of theta, that's equal to y. Those are nice enough to remember because they're the same conversion factors that we had all the way back in trigonometry when we first learned about polar coordinates. So if we put this together, we get that the square root of x squared plus y squared is equal to the square root of r squared cosine squared of theta plus r squared sine squared of theta, which, if we factor out the r squared here, this is going to give us the square root of r squared times cosine squared of theta plus sine squared of theta. But by the Pythagorean identity, that's the number 1. So here that's equal to the square root of r squared times 1. All right, that's the Pythagorean identity from trigonometry. And so now the square root of r squared is just equal to r. Normally, we'd have to worry about signs here. Is this positive? Is this negative? But remember, here we want everything positive. So we're good. So here, the square root of x squared plus y squared, that's just r, which is really nice. Okay, so here our integral is going to equal to, well, let's see, we have a triple integral, just like that. And we're going to want this to be just r. Okay. Now remember, whenever you're converting from rectangular to cylindrical, dz, dy, dx will become r dz dr d theta. Just like that. Here, this r was that integrand. This r is the conversion factor that you get when you convert from rectangular to cylindrical. I've been throwing around the word Jacobian. Our very next section, we'll talk about exactly what the Jacobian is. All right, so now we have all of this converted. Now we just have to worry about these bounds. But since this is a single cylinder with a flat bottom and a curved top, this should be pretty simple to describe. In fact, r and theta is something we already had from our very first part. When we first sketched Q, notice that we started by looking on the xy plane to describe one trace of this object. And then we generated upwards from there. Well, yeah, but this right here on the xy plane is a description in terms of r and theta. We never expressed it that way. We expressed it in terms of x and y. But in terms of r and theta, what are these bounds? Well, you're going to start from r is equal to 0 all the way to r is equal to 2. And theta, that's going to go from 0 to pi over 2. So we already have two of these. Theta is going to go from 0 to pi over 2, and r is going to go from 0 up to 2. That describes this part in red, the base. So now we just have to describe z, the height. Notice it does go down all the way to this xy plane, which means that the height is starting from 0 going upwards. So my lower bound is 0. So really the only work we have to do is to find that upper bound. All right, well, let's see. What is our upper bound? Well, from before we saw it was this thing. All right, it's the upper sphere. Well, yeah, but x squared plus y squared. We saw just a minute ago, x squared plus y squared can be written as r squared. That's a really simple conversion. X squared plus y squared is equal to r squared. So if both of these are negative, well, then it would make minus r squared. Here, using this same idea, the square root of 16 minus x squared minus y squared, that is the equation of this upper bound, can be written as the square root of 16 minus x squared plus y squared, which we see over here. If you take this x squared plus y squared, it converts into r squared. Okay, so that's going to be square root of 16 minus r squared. So that's your upper bound. Which is substantially simpler than spherical coordinates. Now, that's not to say spherical coordinates are always going to be complicated, but whenever your object looks like either a cylinder or a cylinder combined with a sphere or anything else of that nature, cylindrical coordinates are by far going to be easier to work with. Spherical coordinates work whenever you have a portion of a sphere without any straight edges. Then, in those cases, that is a much faster way to go. Right? So here you can see how the initial part 1, drawing out our sketch, can give you a quick way of figuring out, okay, here's the way I want to go. Because if we don't, and we just say, oh, I'm just going to go with spherical every time, well, then it's going to give you some very complicated problem. Oops, wrong one. That's going to give you some very complicated problems sometimes. And likewise, if you always do cylindrical, well, sometimes that will give you something complicated. Maybe spherical is the right way to go. So starting off by drawing your region can save you a lot of work down the line. All right, and now finally part number 4. Let's go ahead and evaluate. Let's say evaluate the integral. All right, remember all three of these representations mean the same thing. If you want to, you can evaluate this one here, the original. That looks unpleasant because I have the sum of squares under a square root, and same thing here, and I have a square in here. That's going to require a lot of trig substitutions. I don't think I want to do that, but I could. If I did this, that is a little simpler to actually do than the previous problem. Now here there'd be 2 integrals to evaluate, so I would have to do it twice and add those together. But it at least doesn't look like I need as many trig substitutions. The reason for that is because the trig substitutions have kind of already been done, if you note. But out of the representations we have, this one clearly seems the simplest. Right? We don't have any trig expressions here at all, at least not yet. And here, these integrands seem a lot simpler to work with than any of the other ones we've had. So all three of them will give us the same answer. So let's go with whichever one's easiest. Here I'm going to evaluate the integral by whichever is easiest, by whichever coordinate system is easiest. And here I contend that this one's probably going to be the best one. So let's do that. The integral from 0 to pi over 2 of the integral from 0 to 2 of the integral from 0 to the square root of 16 minus r squared. Here, let me combine those. R times r, I can just write that as r squared dz dr d theta. At this point, go ahead and give that a try. Take a minute, pause the video, and go through to the end. See if you can find a result. In the end, your result will not look very nice. It's going to involve, I'm not sure I've ever seen this before. This answer involves pi squared. You know, the number pi squared, it's in there. But in any event, go ahead and pause the video, give it a try, and see what you get. Whenever you get a result, go ahead and unpause and we'll go through it together. All right, so let's go ahead and take a look. Starting from the inside, we're going to take this integral. And this integral is easy because that's a constant with respect to z. So here that's going to equal to the integral from 0 to pi over 2 of the integral from 0 to 2 of r squared z from wherever z is equal to 0 up to wherever z is equal to the square root of 16 minus r squared dr d theta. That bracket is that bracket. Here, notice I label z is equal to because when you have multiple variables, it's really easy to plug something into the wrong variable. So here that's going to be the integral from 0 to pi over 2 of the integral from 0 to 2 of, well, multiplying times 0 makes that 0. So we can ignore that one. But plugging this one in will give us r squared square root of 16 minus r squared dr d theta. Okay. Notice that d theta is going to be easy to do, but this dr, the integral with respect to r, is not going to be very nice. I have the difference of two trig functions, which means I still, the difference of two squares, which means I will probably be using a trig substitution here. All right, so let's go ahead and do that. Here, let's go ahead and take just that integral. So I'm going to go to another page. Let me take just the integral from, in fact, let me just take the antiderivative here. Let me take the antiderivative of r squared square root of 16 minus r squared with respect to r. So here's this, just go ahead and do the antiderivative. We'll plug that back in when we get there. All right. Here we need a trig substitution. Here we have the difference of squares where you have a constant squared minus a variable squared. That's a sign substitution. So here we're going to use a substitution that r is equal to 4 sine of theta. All right. It's whatever you squared to get this is equal to whatever you squared to get this times sine of theta. Okay. If that r is equal to 4 sine of theta, that's going to be our substitution. Our differential, dr, is going to be 4 times the cosine of theta, d theta. Oh, and you know what? Let me not use theta because we've been using theta for something else in this problem. So here, let me use the letter u. Let me not confuse matters by using theta for different things in the problem. So here I'm going to use trig substitution. R is equal to 4 sine of u, and dr is equal to 4 cosine of u du. All right. So that's going to transform this into the integral of, let's see here, r squared. That's just the square of this guy. So 4 sine of u squared times the square root of 16 minus that same thing, 4 sine of u squared. And then dr is 4 cosine of u du. Looks like that. Okay. Here we can write this as the integral of, let's see, that's going to be 16 sine squared of u, square root of 16 minus 16 sine squared of u, 4 cosine of u du. Okay. Let's see here. 1 minus sine squared of u is the Pythagorean identity. That's the cosine squared of u. Oh, but these are being multiplied by 16. Okay, so it's 16 cosine squared of u. So this is the integral of 16 sine squared of u times the square root of 16 cosine squared of u times 4 cosine of u du. But I can take the square root of that, so that'll be the integral of 16 sine squared of u times 4 cosine of u times another 4 cosine of u du, which we can write out as, let's see, 4 times 4 is 16, times 16 is 256, times the integral of sine squared of u times cosine squared of u du. Okay, so there's our integral so far. Let's see now. Okay, so now we want to use the half angle, the power reducing formula here, which is going to be 256, the integral of sine squared of u is 1 minus cosine of 2u over 2. And this is 1 cosine squared of u is going to be 1 plus the cosine of 2u over 2 du. Here, we can take the 1/2, factor it out. We can take the other half and factor it out. So 256 divided by 4 will give us 64. Yeah, 64. Times the integral of, and we can multiply these out. 1 times 1 is 1. 1 times cosine of 2u, but then minus cosine of 2u, those would cancel out. And a positive times a negative is a negative. Cosine of 2u times cosine of 2u is cosine squared of 2u. Just like that. Oh, well, that's still got an even power. So let's do it again. Let's use the power reduction formula. This is now going to be 64 times the integral of 1 minus, here, this cosine squared of 2u is going to become 1 plus the cosine of 4u. Remember, whenever you use the power reduction formula, your power reduces by 1, but then your argument doubles. All over 2 du. Here, I can go ahead and combine my like terms. That's going to give me 64 times the integral. 1 minus 1/2 is 1/2 minus cosine of 4u over 2 du. I notice there's a common factor of 1/2. So let me factor out the 1/2, and that'll make this 32 times the integral of 1 minus the cosine of 4u du. And now that's an integral that we can take. So here that's going to be 32 times the integral, not times the integral, 32 times 1 integrated with respect to u, that's just u. And then I'm going to take the integral of the cosine of 4u, although there's a minus there, so that'll be minus sine of 4u. But then, due to the chain rule, I have to now divide by the derivative of this. So that'll be 1 over 4. Right. I can now expand that out, and that'll just give me 32u minus, 32 divided by 4. That's going to give me 8 sine of 4u. Just like that. So, at this point, we have a couple of choices. One is, okay, now we can convert back into R. The other choice is we can just change our boundaries from the very beginning. Note that we had boundaries originally that were from, what were my original bounds? They were from 0 to 2, is that right? Yeah, 0 to 2. Well, if I have bounds from 0 to 2, those bounds tell me what R is equal to. Well, if I just plug them in here, I can figure out what u bounds I would need to be equivalent to this. So here, let's change our variables, frankly, because it's going to be simpler than going back and back substituting all the way. Here, note that if we have r is equal to 2, let me start with 0. If r is equal to 0, then that means that 0 is equal to 4 sine of u. I can divide both sides by 4, which still leaves me 0 equal to the sine of u, which means that u must equal to 0. So here, I can have this as being the bounds from 0 up to, okay, well, let's see what happens if I have r is equal to 2. If r is equal to 2, okay, well, that's going to be 2 equals 4 sine of u, like that. I'm just plugging that 2 in right there. Okay, well, now I can divide both sides by 4, so I get 1/2 is equal to the sine of u, like that. And if I say I want an angle whose sine is equal to 1 over u, well, that's the inverse sine of 1/2, which is pi over 6. So here u is equal to pi over 6. All right, so instead of having r bounds from 0 to 2, I'm going to have u bounded from 0 to pi over 6. Pi over 6. So that's from 0 to pi over 6, 0 to pi over 6, 0 to pi over 6. All of these. So now we won't even need to back substitute. We just plug these numbers in directly. All right, so let's go ahead and give that a try. That's going to be 32 times pi over 6 minus 8 times sine of 4 times pi over 6 like that, minus 32 times 0 minus 8 times the sine of 4 times 0. Okay, well, those are 0. All right. If I take 4 times 0, that's 0, and the sine of 0 is 0. And same thing here. 0 times 32 is 0. So this whole thing goes away. This whole thing is 0. All right, so now just this part right here. If I take 4 times pi over 6, that's the same as 2 pi over 3. And if I take the sine of 2 pi over 3, I get root 3 over 2. So this gives me 32 times pi over 6 minus 8 times root 3 over 2, like that. Oop, you guys can't see that, can you? There we go. So that I just brought that down, minus 8 times the sine of 2 pi over 3. Right, these are being multiplied. The sine of 2 pi over 3 is root 3 over 2. And now I can go ahead and clean that up. 32 over 6. That's the same as 16 over 3 times pi. Oh, let's see here. 16 over 3 times pi minus 8. Oh, I guess 8 divided by 4. 8 divided by 2 will give me 4 root 3. So that is the integral from 0 to 2 of r squared square root of 16 minus r squared with respect to r. It's going to be 16 pi over 3 minus 4 root 3. So coming back over here, I can just write this as equals to the integral from 0 to pi over 2 of, here, the integral from 0 to 2 of r squared square root of 16 minus r squared dr. We found that that was 16 pi over 3 minus 4 root 3. Okay, so this whole thing here just becomes this number here, 16 pi over 3 minus 4 root 3, like that. And finally, we're just about done. Notice that's a constant. And if you integrate a constant with respect to theta, you just get that constant times theta. So here, let's see, that's going to equal to the 16 pi over 3 minus 4 root 3, all of that times theta. evaluated from 0 up to 2 pi. Oh, not 2 pi. Pi over 2. Obviously, if you multiply times 0, nothing happens. It's just 0. So here the only one that matters is pi over 2. So in the end, our answer will be 16 over 3 pi minus 4 root 3 times pi over 2, which I can distribute to give me, let's see, 16 pi times pi. That's going to give me, here. So 16 over 2, that's going to give me 8 over 3. Pi times pi is pi squared. So 8 over 3 pi squared. And one of the few times I've ever seen pi squared in an answer. Minus, let's see, 4 goes into 2 twice. So that's going to be 2 root 3 times pi. And there's a minus there, so minus 2 pi root 3. And there we go. So this is our last result. We've integrated our original problem. We developed it a few different ways, and it looked like this one was the one that was the most straightforward. It was not completely straightforward because obviously from here to here there was a lot of work, which we did on its own separate page here. But this is a difficult problem at the very beginning. So it's not unreasonable to assume that even if you do convert it into a simpler form, even if you do convert it into, in this case, cylindrical was easier, it's still not necessarily going to be extremely simple. Right? So that is it for the section. And let's see, for an assignment, go ahead and try problems. Section 14.7. Go ahead and try problems 11 through 19 odd. The first few are just sketch out some objects, sketch out what this looks like. There's not going to be too much computation. And then for the computational ones, I've only chosen some that ask you to do it one way. They're not going to ask you to do the long process we did here. It'll ask you to do just cylindrical or just spherical. Or if it asks you to just do something, it'll tell you to integrate. It'll be up to you to pick which one you like. And again, I suggest you start off with an illustration, with a sketch. That often tells you which one should be simpler. So 11 through 19 odd. Go ahead and try 23, try 31, and try 43. And that'll suffice. If anybody has any questions, please reach out to me, let me know, and I'll help you with what I can. And I hope everyone has a nice day.